We're going to look at functions and function notation. We'll introduce function notation first and what functions are with a couple of quick examples, and then we'll get into some more detailed examples. To start, we're going to look at something you're already familiar with, square roots. So what is the square root of 16? Now, some of you might say plus or minus 4, but mathematicians agree that the square root of 16 is only 4. Okay, and we're going to talk about why we agree that. So why do we not do plus or minus 4? Well, because when we see a symbol on a piece of paper or in a textbook, we want to think that this will only give us one output. Okay, so the square root of 16, if I say the square root of 16 to one of my mathematical friends, they'll know that I'm only talking about the number 4. They won't say, well, does he mean positive 4 or negative 4? Okay, if we want to write negative 4, if we want to give our mathematician friend an answer of negative 4, we would write negative radical 16, or we'd probably just tell them negative 4, but that's beside the point. Okay, well, what about the absolute value of negative 28? What is that value? Well, there are rules that we know about absolute values. One way you can interpret an absolute value is how far is that particular number from 0. Another way you can interpret it is that if the number is positive, we leave it alone, and if the number is negative, we find its opposite or drop the sign. So the answer is 28. But what I really want to focus on here is the symbols. We have some symbols here that tell us to do something to a number. Hey, what number do I square to get 16? What positive number do I square to get 16? Hey, what is, or how far is negative 28 from the number 0? So that's what these are doing. And so what these are each types of functions. We're assigning exactly one value to this particular expression. We assign one value to the square root of 16 and one value to the absolute value of negative 28. So we're going to go a little bit abstract here. Give me just a moment. What is a function? It's a function from a set A to a set B, and it's just a rule that assigns a single value y in B to each value x in A. So that's very abstract. So how do we want to interpret that? Pick a number that comes from the set A. We're going to assign it some number from the set B. So if I'm talking about a function that represents the square root, if I pick 16 out of the set A, it assigns to the square root of 16 the number positive 4. If I pick negative 28 out of the set A, and we're having to talk about the absolute value function, then we're going to assign positive 28 from the set B. Okay, a few more terms that we won't really get into much here, but they're handy to know. A is called the domain, and B is called the codomain. And then if we look at only the y values that come out of B, these are what are called the range. Okay, so the range is only the numbers that are produced by applying the function to values in A. Okay. If x has been assigned the value of y for some function that we'll call f, we're going to write f of x equals y. Now that seems like unusual notation, but it's simply because we don't want to have to write a new set of symbols every single time we create a new function. Wouldn't it be strange to have to draw a new set of symbols if I want a function that gives me the square of a number or a function that gives me 4 less than the square of a number? I'd have to have a whole new set of symbols. And so we'll just use letters to represent that. That's why we choose f of x as opposed to creating some new set of symbols. So let's look at some examples here. The first one we're going to do that kind of a, how do we say this? It's an intuitive way to look at a function. N is an integer. Now remember the integers are 0, plus or minus 1, plus or minus 2, and so forth. We're going to define next of n to be the next largest integer. And that's the way we read this. We read our function name next in this case, and then the parentheses we say of n. So next of n is just the next largest integer. We want to find each of the following. Next of 101. Well, what's the next largest integer after 101? 102. Okay. Next of negative 416. Now we have to be a little bit careful here because it is a negative number. The next largest integer is one more than that integer, which would be negative 415. And in general, what would next of n be equal to? Well, we just want one more than n, so next of n would be n plus 1. And so often we'll represent our functions by algebraic expressions that represent what we want them to do to our number. Here's an example. Suppose our function is the function that takes each number x and assigns it the value 3x squared minus 5 times x. Okay? So we would first want to find what f of negative 2 is. Now I've used some colors here to help us follow along. What this means is negative 2 has replaced the position of x. So if I've replaced this x by negative 2, I'm going to replace all other x's by a negative 2. So f of negative 2, instead of saying 3x squared minus 5x, it's going to be 3 times negative 2 squared minus 5 times negative 2. And now we can do some simplification. Negative 2 squared is positive 4. 5 times negative 2 is negative 10, but if we subtract negative 10, that's the same as adding 10, and we end up with 22. How about something a little bit uglier, a fraction? F of 2/3. Okay, well, again, we'll color 2/3. F of 2/3 is 3 times the quantity 2/3 squared minus 5 times 2/3. Again, notice we're just taking the x values that are up here and replacing them with the number that's in the parentheses. And now we can work this out. When we square a fraction, we have to square its numerator and denominator. So 2/3 squared is 4/9. 3 times 4/9 minus, if we multiply the 5 by the 2, we end up with 10/3. We reduce here. 3 times 4/9, the 3 and the 9 will reduce. Okay, they both have a common factor of 3, so 3 times 4/9 reduces to 4/3. 4/3 minus 10/3 is negative 6/3, which reduces to negative 2. One final example with this function. Remember, this is the function 3x squared minus 5x. We're going to look at f of 2t plus 1. Now that seems odd. We have a variable x in our original function, and now we throw a new one in. Yeah, well, it's sometimes important for us to do. Okay, so remember our function was 3x squared minus 5x. We've just replaced all of our x's by 2t plus 1. Now we can use a little bit of algebra to simplify. If you know the formula for squaring a binomial, 2t plus 1 is a binomial, you can use that, or you could expand it out. All right. I could have distributed the 5 through here. I eventually do that. We're going to multiply the 2t plus 1 by itself. Don't forget that we have these inner terms and outer terms to deal with. So 2t times 2t is 4t squared. 2t times 1 and 1 times 2t are each 2t, which add up to 4t, and 1 times 1 is 1. All right, now we'll distribute in both circumstances. We'll get 12t squared plus 12t plus 3, and then distribute negative 5 through negative 5, or negative 10t minus 5. In our final example, we're going to look at something that's known as the difference quotient, something you might see if you end up taking calculus. Oh, we didn't simplify our last one here, so there's our simplified version. Okay. So our function this time is 4 divided by x. F of x is 4 divided by x. We're going to do a couple of examples here. What is f of negative 12? Well, remember, all we need to do is wherever I see an x here, I'm going to replace it by my input here, negative 12. We think of that negative 12 as the input and the answer as the output. So f of negative 12 becomes 4 divided by negative 12, because it's 4 over x, I replace x by negative 12. And 4 divided by 12 reduces to 1/3. I'm just going to pull the negative sign out front. So f of negative 1/12 is negative 1/3. Well, now we're going to look at something that is common to see in calculus. Rather than just have something like f of 2t plus 1 like we did in the previous example, we might do something with that quantity. And here we're doing something with it. We're finding f of 1 plus h, so there's a variable in there, and we're subtracting f of 1. After we do that, we divide everything by h. Now I've colored things early this time because I didn't want to have to retype that, really just to save space. Okay, so the first thing we'll do is we're going to look at what f of 1 plus h is. Well, f of 1 plus h, if f of x is 4 over x, we're going to replace x by 1 plus h. So that becomes 4 over 1 plus h. F of 1, on the other hand, is going to become 4 divided by 1, minus 4 over 1. So this first term here is f of 1 plus h. The second term is f of 1, and we're dividing this by h. Okay, so now what we're going to do is we're going to simplify this, and to do so, notice that 4 over 1 just reduces to 4. I'm going to multiply by 1 plus h in the numerator and in the denominator. Okay, it's not very pretty here. There we go, 1 plus h. Okay, now when I do this, we need to distribute to both terms. So we're going to distribute it to the first term and to the second term. Okay. When I distribute it to the first term, the benefit of doing this, I really didn't explain why I chose 1 plus h. I chose 1 plus h so that it would cancel with the 1 plus h that was in the denominator here. When I do that, I'll just end up with 4 because the denominator has reduced. And then this, remember we said 4 over 1 was 4? We have to distribute 1 plus h to 4, so it's going to be 4 times 1 plus h. In the denominator, we still have the h, and we have 1 plus h here. Okay? So if we distribute, we will have 4 minus 4h, or minus 4 minus 4h. 4 minus 4 minus 4h. We can simplify a little bit. Notice that 4 minus 4 is equal to 0. So the numerator will just be left with negative 4h, and I put the negative out front. So we'll have 4h divided by h times 1 plus h. The h's will reduce, and we just end up with 4 divided by 1 plus h.